Around 230 years BC, so over 2,000 years ago, Eratosthenes proved that the Earth was round, that the surface of the Earth wasn't flat, and he even worked out the circumference of the planet to within 2% of what we know it is to be today. And he did all this by looking at shadows that the sun was casting, and by using information that he found in scrolls in the Library of Alexandria. Now, when I say library, I'm not talking about a library where you just go to borrow books. I'm talking about a great store of information. And back then, over 330 years BC, there was very few libraries around, and the one in Alexandria was the greatest on the planet. It had scripts from Persia, from Arabia, from all over Europe, all copied and stored in this one location. If you were on a boat and you arrived into Alexandria, the port authorities came on board, they seized all your books. They were taken to the library and copied, and you would be given back copies of your own books, but the originals would stay in the Library of Alexandria. So the aim was that there would be a copy of every single book in existence in this library. So it was a really, really amazing place and a real store of knowledge. If you can imagine, like, the internet still existed back then and Google still existed back then, but there was only one iPad on the entire planet, and you controlled that iPad. Imagine how powerful you would be. All the things you would know, all the science you would know that other people didn't. Now, it was in one of these scrolls in this library that Eratosthenes read about a city to the south of Alexandria called Syene. And in this there was a record that on the shortest day of the year, on June 21st, at midday, in Syene, there were no shadows anywhere. So all the pillars in the town, or if you held a stick vertically, there would be no shadows because the sun was so directly overhead this town on the shortest day of the year. Eratosthenes wondered, does the same happen in Alexandria on June 21st, the shortest day of the year? And he did an experiment, and he found that on that day, at the highest point of the sun, at noon, in the middle of the day, yes, there were shadows in Alexandria. How could this be? That there were shadows in Alexandria, but there were no shadows in Syene? To figure this out, we're going to have to go to Egypt. This is a map of ancient Egypt. We have the Mediterranean Sea, we have the city of Alexandria, and down the River Nile, we have the city of Syene. Now, I'm going to build two little columns in each of the cities. Now, the ancient Egyptians were really good builders. They not only built pyramids, but they built obelisks and columns all over their cities. And they were perfectly straight. There was no leaning on these. So now I'm going to take this outside into the sunshine. Now, I'm outside in the sunshine. I'm holding my map perfectly flat, and I've angled it so that the column is directly pointing at the sun, so there's no shadow at the column in Alexandria. And if I look at the city of Syene on my map, again holding it perfectly flat, it's pointing directly at the sun and there's no shadow cast by my column. And this all makes sense if the earth is perfectly flat, just like my map is. There's no shadows at either column because the sun is directly overhead. But if I angle my map to the sun, look, both columns are showing shadows at an angle and they're about the same. And again, this makes sense as long as the earth is flat, just like my map. But watch what happens when I bend the map in just the right way. Now the column in Syene is pointing directly at the sun and doesn't cast a shadow, but the column in Alexandria casts a long shadow. This is exactly the same as Eratosthenes saw. So the records of the no shadows in Syene on the shortest day of the year and shadows being cast in Alexandria on the same day can only make sense if the earth is a curved surface, just like the curved surface of my map. Eratosthenes was not the first person to suggest the Earth was a sphere. Pythagoras had suggested it as well, but he had no proof. But Eratosthenes now had an experiment that could be repeated again and again in different locations that proved that the Earth was a curved surface, that the Earth was a sphere. He also very cleverly measured the length of the shadows that he saw in Alexandria, and he was able to work out that the sun must be hitting the top of the column at an angle of about 7 degrees. Now, the Earth is so far away from the sun that all the rays of light coming from the sun are coming parallel. So the ones hitting the column in Syene were hitting it parallel to the column, so it cast no shadow. It was at 0 degrees. But the rays of light hitting the column in Alexandria were hitting it at an angle of about 7 degrees and causing a shadow. By measuring the length of the shadow on the ground and knowing the height of the column, he was able to work out the angle as 7 degrees. We know that a circle has 360 degrees, and Eratosthenes had figured out there was 7 degrees of difference between Alexandria and Syene. So what fraction of 360 degrees was that 7 degrees? So how many times can 7 degrees divide into 360 degrees? So say, for example, if I had a cake and I wanted to cut it into slices that were 7 degrees, how many slices of cake would I get? Well, 7 divided into 360 gives an answer of 51. There's a remainder of 3, but 51 is a reasonable number. So if I cut a cake or a pizza and each slice is 7 degrees, I'm going to get 51 slices. So it's the same with the Earth. I've cut up the Earth into 51 slices, but how big is each one of those slices? And can I figure it out? So if I can figure out what the length of one slice is, I can figure out what the length of 51 slices is, and I can figure out what the length of the entire Earth is, or what the circumference of the entire Earth is. But how am I going to figure out the length of that one slice? For Eratosthenes, that slice was the distance between Alexandria and Syene. That was the distance he had to work out, but he couldn't go to a map. That's what he was doing. He couldn't just look up the distance. He had to figure it out. He actually had to pay a man to pace the entire distance between the two columns, starting in Alexandria, walking all the way south, counting every single step to work out what the distance was. Didn't matter if people got in the way, if you had to climb over hills or valleys or rivers, the man had to walk as straight as he could and constantly count all his steps to try and pace out the distance between the two cities until he eventually reached the other column in Syene. By the time the man reached the column in Syene, he'd walked 5,000 stadia, the ancient Greek measurement. That equates to 800 kilometres today. So, Eratosthenes had divided the world into 51 slices, and we now knew that the length of one of those slices was 800 kilometres. So it was simply a matter then of multiplying 800 kilometres, the length of one slice, by 51 slices to see what the length of the entire Earth, or the circumference of the entire Earth, was. This picture was taken by the Apollo 17 astronauts on the way to the moon, and it's one of millions of pictures that we've now taken of the Earth from space. And from all those pictures, we can work out a very, very accurate circumference of the Earth, and it turns out to be 40,030 kilometres. So Eratosthenes was only 770 kilometres out when he came up with his number over 2,000 years ago. That's less than a 2% error. Hopefully you enjoyed that, and now you know just one of the reasons you could explain to somebody that no, we don't live on a flat Earth, And we've known this for a very, very long time.